Hey everyone, let's take a little bit of a look at something different. We've talked a lot about X and Y motion, but what I want to show with this is angular motion. The concepts will still be the same. In fact, the equations will actually look the same as one-dimensional motion, except everywhere we had position, we're going to say angular position. All right, so let's say I've got this axis here, and I've taped that off, and that's just my reference point. And so let's call that the positive x-axis, if you will, but it's the 0 degrees motion, or the 0 degrees position. As this thing rotates away from that 0 degrees position, this line is measuring a new angle, right? So if 0 is where my finger is, and I've gone through this angle as I've gone through this circular motion or this angular motion, right? And so as I move, I'm changing my angle. And I can move slowly, and the angle changes with respect to time with a small angular velocity, a small rotational velocity, if you will. Or I can rotate more quickly, and I have a larger angular velocity. Same idea. I can go counterclockwise. We're going to consider that positive angular velocity, or I can go clockwise. We'll consider that negative angular velocity. Right, so the derivative of the angle with respect to time, or the angular position with respect to time, will give us this velocity. And we're going to call that angular velocity. And it's d theta dt. If theta is the angular position, d theta dt is degrees or radians, then dt is per second, right? It's seconds, but it's in the denominator. So that would be radians per second. Now that's neither mass, length, or time, so that's actually dimensionless in the numerator. Radians and degrees has no dimension. It's not mass, length, or time, but it is an angular position, but we don't consider that dimension. And so the angular velocity, let's say radians per second, would also be written as seconds to the -1, okay? All right, right now it's not moving, and I give it a push. Now it has an angular velocity. There must have been an angular acceleration. And if I push this and let it go, you'll see it slow down or speed up. Probably going to slow down because of friction. The angular velocity is changing. And as the angular velocity changes, there must be an angular acceleration. So d, second derivative of theta with respect to time, and you can see it stop there. The second derivative of theta with respect to time is an angular acceleration. D squared theta, radians, dt squared, second squared. So radians per second squared, or seconds to the -2. So all the stuff that we did in the case of linear positions, especially one-dimensional, we can do here, angular position. And it's either positive, counterclockwise, or negative clockwise. It really is one-dimensional, if you will. D theta dt, we use the Greek letter omega for that. That looks like the funky W with a tail. D squared theta dt squared, we use the Greek letter alpha, looks like a fish, for the angular acceleration. All right, same names except just put angular in front of it. Position, angular position. Velocity, angular velocity. Acceleration, angular acceleration. And later on in the course, we'll actually look at angular forces and angular energies and angular momentum. All of those things will return in an angular format, and we'll get to that later on. All right, so here you go. Angular velocity, wait a few seconds, and we can see it slowing down. There must be an angular acceleration. And it's slowing down, so the angular acceleration is negative if the angular velocity is positive. If I go the other direction, angular velocity is negative, but it's slowing down, so the angular acceleration must be positive. If it's slowing down, then the angular velocity and the angular acceleration are in a different direction. If I push it, I'm giving it an angular acceleration in the same direction as the angular velocity, and it's speeding up, right? So they're in the same direction. Now it's slowing down because I'm not exerting that angular force any longer. All right, you can see it slowing down. All right, that's good for now, and we can put some equations up later on.